Deploying agents in real products involves integrating AI systems into practical applications where they interact with users or other systems. This stage is crucial because it tests the agent's reliability, scalability, and usefulness in real-world scenarios. Understanding deployment challenges helps ensure the agent performs well beyond controlled environments. This part explains how a software project evolves from an initial prototype into a fully mature production system. Understanding this progression is crucial for managing complexity, ensuring reliability, and scaling the solution effectively. This part explores the crucial transition when a model moves from a simple demonstration to becoming a reliable part of a real-world system. Understanding this shift reveals why deployment involves much more than just showing a model's capabilities. A prototype agent can appear fully functional when tested in a controlled environment like a local notebook or a small web demo. These settings are forgiving because the user is patient, inputs are curated, and failures can be manually fixed. However, once the agent is deployed behind a product interface, the environment changes drastically. It must handle real traffic, unreliable upstream systems, and diverse user needs, which makes the problem much more complex. Deploying an agent is no longer just about packaging a model with an endpoint. It becomes an operating environment where reasoning, tool use, state management, and user expectations interact with infrastructure constraints. The model remains central, but the system's behavior depends equally on factors like latency limits, retry policies, and tool availability. A demo highlights capability, but a production service reveals how capability interacts with real-world conditions. The Atlas Travel Assistant illustrates this shift clearly. In prototype form, it can research flights and recommend options for one user in one session. In production, it must handle slow APIs, inconsistent tools, cancellations, concurrent requests, and returning users expecting continuity. The agent's identity stays the same, but its job expands from producing one answer to sustaining a reliable service relationship over time, which is the true measure of deployment maturity. Deployment should be seen as a systems engineering challenge, not just a demonstration of intelligence. The goal is to embed the model inside a service boundary that can detect, contain, and improve its behavior as it faces real-world conditions. Monitoring, resilience, structured outputs, serving strategies, and cost control all answer the same question. What must be true for the agent to keep functioning reliably when users depend on it? Prototype assumptions often fail when exposed to real-world traffic because the conditions in testing are much simpler and less demanding than in production. Understanding these differences helps us design more robust systems. A delay that seems acceptable during a single test can become a serious problem when users face it repeatedly throughout their entire journey. Each wait adds up, making the experience feel slow and frustrating, which can cause users to abandon the product. Failures that seem minor or infrequent in a prototype can have much bigger consequences in production. They disrupt users, corrupt workflows, and increase support demands. Even a small failure rate can create a constant operational challenge that a product must manage carefully. Unlike controlled demos, real traffic includes ambiguous inputs, unexpected formats, and long interactions that reveal weaknesses in the system. Handling the average case isn't enough. The system must also manage these edge cases that drive support costs and user trust. In production, immediate human intervention isn't always possible or practical. The system must operate reliably with minimal manual fixes, balancing intelligent behavior with the operational impact on infrastructure, maintenance teams, and users. This part introduces a maturity model that helps us understand the stages of deploying an AI system. It breaks down deployment into clear phases, making it easier to track progress and risks. A maturity model provides a more exact language than just saying a system is ready or not. The first stage, often called the fast MVP, aims to test if the concept can actually work and deliver value. At this point, the team isn't trying to make a perfect product, but to learn if the agent can do something useful. The biggest risk here is becoming overconfident because a limited demo might look better than it really is. Success means gaining real insights about what's feasible, how it fits with other systems, and what users find valuable. This figure maps the deployment journey as a progression through several stages. It starts with feasibility testing, moves to learning from real users, then hardening reliability, taking on production responsibilities, and finally scaling capacity to handle growth. Each stage builds on the previous one. At the alpha stage, the system starts interacting with real users, which helps reveal unexpected problems that didn't show up in control tests. The team uses this phase to identify which parts of the agent work reliably and which require changes. The main risk is that the system might be exposed too widely before it's ready. Success means having a clear understanding of how the agent behaves in real conditions and where the product limits should be set. The beta stage shifts focus from finding new problems to minimizing known ones. The team develops operational controls and safer defaults to make the system more predictable. It's important not to confuse increased usage with true readiness. Success here means the system behaves reliably enough to be used widely without needing to handle exceptions on the fly. Production means the system is no longer experimental, but a dependable service. Users expect it to be continuously available, support teams become important, and other systems may rely on its output. The biggest risk is failures that affect the wider business. Success requires clear documentation, fallback plans, support structures, and a defined line between normal issues and serious incidents. Scaling a system is different from just putting it into production. Scaling introduces pressures like handling more requests, controlling costs, planning capacity, and managing a wider range of operations. The main risk often involves economics. Working correctly isn't enough if the system becomes too expensive or slow at scale. Success means the service stays reliable and predictable as demand grows. Teams must demonstrate both readiness and the ability to grow sustainably. You can think of the maturity model as a series of questions that change over time. First, can the idea actually work? Then, what breaks when real users start using it? Next, what controls are needed to build trust? After that, can the system handle real responsibility? Finally, can it sustain that responsibility as it scales? This model helps teams understand how the evidence they need to build confidence evolves through deployment. A fast minimum viable product, or MVP, should be seen as a diagnostic tool rather than a final promise of the product. This approach helps teams focus on learning and understanding system behavior early on. Treating the first live version like a mini product launch often leads to misplaced priorities. Instead, the MVP should act like a lab experiment, revealing how the system behaves in realistic but controlled settings so the team can learn rapidly. For example, Atlas's MVP might support just one specific trip planning flow with a small user group and a couple of tools. The goal isn't to build the full product, but to find out if the agent interacts well with search, if users understand its suggestions, and if response times are acceptable. The idea of minimum viable product is often misunderstood. It's not about having many features, nor is it about rushing carelessly. Instead, the MVP should be minimal where it doesn't affect the hypothesis, but realistic where it matters most to gather meaningful evidence. Unexpected issues like brittle prompts or slow responses aren't just bugs to fix quietly. They provide valuable data about the system's limits and design assumptions. The MVP's value lies in exposing these weaknesses early, making the first deployment a critical learning stage. Alpha testing moves the system beyond controlled environments and into real-world use. This stage uncovers unexpected behaviors and challenges that only appear when real users interact with the product. When the system leaves the lab, it encounters a wider range of user behaviors. Internal testers often follow known paths, but real users try things the team never expected. They jump between tasks, interpret meanings differently, and care about outcomes the designers didn't plan for. This is where hidden assumptions come to light. For example, a limited release to a small group of travelers or employees lets the team observe how people really use the assistant. Users might expect the system to remember details from earlier conversations or interpret suggestions as promises. These nuances often cause frustration or confusion that scripted tests miss. The team learns that quality depends not just on correctness, but on managing expectations and conversational flow. The system might complete tasks correctly, but users can still feel uncertain or misled. This mismatch is critical because it affects trust and satisfaction. During alpha, elements like error messages, tool limits, and how quickly the system responds can be adjusted. The team is shaping the contract between the user and the agent, not just fixing bugs. Alpha is not a guarantee of quality. Many issues remain unstable by design. This stage accepts imperfection because the goal is to learn. Forcing alpha to act like production removes its value as a diagnostic tool, while treating it as a harmless demo risks ignoring real problems. The right balance is to reveal enough reality to learn from, while limiting the impact so the team can respond effectively. Hardening and beta phases focus on transforming experimental capabilities into dependable, consistent behavior. This part explains how teams shift from exploring possibilities to building trust through predictable performance. Hardening starts once the team has enough data to focus on the most important failure modes instead of exploring every new idea. The work changes from discovery, which asks what the system can do, to hardening, which asks how to make that behavior reliable enough for wider use. Discovery opens options, hardening narrows variance. Beta represents the stage where the system isn't finished, but behaves more consistently and fits better with other workflows. For example, booking actions might be limited to approved paths, and responses become more carefully phrased. The focus shifts from whether the agent can do a task to whether it can do it dependably enough to earn user trust. At this stage, the team accepts that some actions will fail or produce unusable results. The design changes to expect degraded operation rather than perfect success. If the agent can't complete a request as intended, it should still leave the user in a state where recovery is possible, avoiding confusion or dead ends. Early on, occasional success might be enough, but beta demands consistent results for similar inputs. This requires tighter control over prompts, tools, and outputs. More importantly, the team treats variance as a cost, recognizing that unbounded creativity can become noise. Hardening means turning impressive but unpredictable behavior into reliable utility. Beta acts as a transition from creating new capabilities to running a dependable service. It reveals how much variability the product can handle, what failures are acceptable, and what guarantees are needed before users will trust it. If alpha shapes the problem, beta locks that shape into a reliable system. Production and scale represent two distinct challenges in system deployment. Understanding how they differ is crucial for building reliable and efficient services. Production readiness means the system is accountable for real users, support, and operational demands beyond just engineering. Scale, on the other hand, focuses on handling increased volume and traffic without breaking or becoming too costly. Simply launching a system to users doesn't guarantee it's truly production ready. A production service must be dependable, with clear failure behaviors and integrated support processes to ensure the business can rely on it consistently. As usage grows, the system must not only remain correct and available, but also cost-effective. Latency and retries that seem minor at low volume can multiply cost dramatically when scaled, making efficient design essential. Increasing traffic often exposes bottlenecks and dependencies that weren't apparent before. Queues form, delays accumulate, and support demands rise, showing why production and scale require separate planning and strategies. A robust deployment approach recognizes that launching a product isn't the same as supporting it responsibly or scaling it economically. The system must first prove it can operate reliably before it can prove it can grow sustainably. This part explains a practical cycle for improving agent deployment. It shows how teams can continuously refine their systems by building, observing, hardening, integrating, and optimizing in a repeating process. Deployment maturity works best as a loop rather than a straight path. Teams create a version of the agent, watch how it performs in real conditions, improve the parts that fail, connect it to other systems, and then optimize for whatever new challenge appears. This cycle repeats because each step reveals new issues that weren't obvious before. This figure outlines the loop visually. It starts with a small build, then observing how the agent behaves in practice. Next comes hardening the fragile parts, integrating the agent into the larger product, and finally optimizing the system to tackle the next bottleneck that appears. The build phase focuses on creating the simplest version of the agent that can reveal the next key insight. It's not about piling on features, but about targeting a specific question or hypothesis to test. Observation transforms the built version into data. The team watches how the agent actually behaves under real conditions, noting where it stalls, surprises users, or fails often enough to matter. This step converts a running system into a learning system. Harden means responding to observed problems by changing designs, setting operational limits, or applying safer defaults. Integration ensures the agent works smoothly with other products and processes. Optimization then makes the system cheaper, faster, or more stable, but only after understanding what really matters from observation. This loop helps avoid two common mistakes: endlessly tweaking prototypes without real-world tests, and rushing broad releases that treat every problem as urgent. It promotes gradual exposure and reminds teams that maturity builds up over cycles, reducing uncertainty and improving control. Understanding the difference between monitoring a live system and evaluating its quality is crucial. These two activities focus on different questions and serve distinct purposes in managing an agent. Monitoring looks at how the system is performing right now. It checks if the service is up, if response times are changing, if failures are clustering, or if traffic patterns are unusual. This continuous process helps ensure the service is stable and operating as expected. Evaluation measures how good the agent is according to defined standards like task success, accuracy, or safety. It often happens offline or in controlled settings and compares different versions or approaches. This process focuses on quality rather than just current behavior. A system might appear healthy on monitoring dashboards with good uptime and latency, but still frustrate users with poor outputs. Conversely, a model might score well in evaluations, yet fail in live conditions due to brittleness or cost issues. Monitoring and evaluation answer different questions, and both are essential. For example, monitoring might detect slowdowns or increased failures in a travel assistant during busy times, while evaluation might reveal declines in recommendation quality or overly cautious language. Mature deployment requires both types of evidence, and teams must not treat them as interchangeable. This part explains how the Atlas Travel Assistant evolves through different deployment stages, maintaining the same core system while adapting to new environments and user needs. At the local demo stage, Atlas acts as a proof of concept. It shows that the assistant can understand travel intent, call a search tool, and offer a coherent recommendation. The environment is controlled, so the team can quickly fix any mistakes, focusing mainly on validating the basic control flow rather than full service behavior. In the diagnostic MVP phase, Atlas moves into a live setting but with a narrow focus, like a small user group or a single trip planning scenario. This stage reveals how the system handles real-world challenges, such as imperfect inputs and slow services, helping the team understand how Atlas behaves beyond the ideal demo environment. At Alpha, a broader but still controlled group of real travelers interact with Atlas. Their varied behaviors expose edge cases like changing dates or incomplete itineraries. This interaction turns the assistant into a source of design insights, showing where language needs clarity and where the user journey can be simplified. When Atlas reaches production readiness, it must operate reliably and predictably. The assistant needs to handle failures gracefully, maintain user trust, and meet service expectations. The focus shifts from proving travel logic to sustaining it at scale without compromising the product experience or costs. This part focuses on how to judge the readiness of a system using clear signals and a simple maturity checklist. Understanding these signals helps decide when a system is ready for more responsibility. A prototype might look impressive, but if it only works when carefully guided or if its success can't be repeated reliably, it remains immature. The key is whether the system's behavior can be consistently reproduced under conditions similar to real use, not just whether it performs well once. When a system reaches the pilot stage, it starts showing consistent user behaviors that the team can observe and understand. The focus shifts from solving every edge case to recognizing recurring failure modes and knowing which parts can be safely automated versus where human oversight remains necessary. A production-ready system delivers consistent outcomes for similar requests within acceptable variation. The team anticipates likely failures, knows fallback procedures, and understands service ownership. If constant manual fixes are needed, the system isn't ready. True readiness means handling routine changes without improvisation. The maturity model helps by focusing on the kind of evidence that justifies each stage. Prototypes prove feasibility, pilots provide real user insights, and production demands repeatability and support. Scaling up adds the challenge of keeping these properties affordable. Progress means trusting the system with more responsibility based on solid evidence. Understanding the MVP as more than a smaller version of the final product changes how we build and evaluate it. This part explains why the MVP should be seen as a tool for learning about the system's real behavior, not just as a demo. Instead of judging the MVP by whether it satisfies users like the final product, think of it as a diagnostic lab. It reveals how the system performs under real conditions, including where it struggles or assumptions fail. For an agent system, this distinction is crucial because real users and unpredictable inputs expose behaviors that a simple demo can't show. This figure illustrates the MVP as a diagnostic instrument rather than a smaller product. Focus on how it uncovers system behavior when faced with real-world challenges, such as user interactions and varying conditions, rather than just showing polished features. The MVP remains valuable beyond the initial demo because its smaller scale makes it easier to analyze. Large products have failures scattered across many parts, making problems hard to trace. But a focused MVP lets us pinpoint unexpected behaviors and link them directly to specific prompts or decisions, much like how a microscope reveals hidden details. Maturity in an agent system isn't just about adding more features. A demo shows the system can work once, but a diagnostic MVP lets us observe and debug it repeatedly. A pilot tests real users safely, and production readiness requires trusting the system's behavior even without constant monitoring. This progression is about making the system's actions clear and understandable. For the Atlas Travel Assistant, the MVP evolves from a simple demo to a diagnostic tool that exposes when complex tool use strains the system or when it drifts from its intended role. These insights don't just improve the product, they shape what the product really is. The MVP becomes the first place where the system's identity is measured through its behavior. Agent systems behave in ways that depend heavily on their runtime environment. Understanding why they need real-world observation helps us see why testing alone is not enough. Even when the model, prompt, and tools remain constant, agent behavior can change because the environment where they run is never exactly the same. Users phrase requests differently. Context windows change size. Tool response times vary, and external data can be incomplete or ambiguous. This means the agent operates in a control loop that reacts to these runtime variations, not just producing text in isolation. Because agents respond to changing conditions, teams must watch how they perform in real usage, not just rely on handcrafted tests. Local tests confirm that prompts are coherent and tools callable. But real-world interactions expose Messier problems like users changing goals mid-session or tools returning ambiguous data. These issues often look like plausible but incorrect behavior, which is harder to catch and more dangerous than outright errors. Traditional monitoring like uptime and error rates still matter, but they miss subtle failures in agents. An agent can be running smoothly, yet break role boundaries, ignore policies, or drift into unstructured outputs. This silent behavioral drift makes the system less trustworthy, even though it appears healthy from an infrastructure view. Only observing real-world behavior can catch these issues before users accept them as normal. This figure illustrates how agent observability integrates infrastructure metrics like latency and error rates with behavioral signals, such as policy adherence and output structure. Traces sit at the center, linking these signals to understand the root causes of issues in agent behavior. In the Atlas Travel Assistant example, simple trips involve few tool calls and short reasoning, while complex itineraries require many searches and constraint checks. These complex cases expose issues like style shifts or schema breaks that simpler cases never reveal. Observing real-world use captures these rare but critical behaviors, which are where assumptions about normal operation fail and problems arise. This part explains what kinds of problems the diagnostic lab aims to find in an agent system. It focuses on subtle issues that don't always show up as clear errors, but can still affect performance and reliability. The diagnostic lab's purpose is to catch early warning signs that might not look like typical errors. An agent's response can be technically correct but still wrong in important ways, like using the wrong labels or acting outside its intended role. These hidden issues can degrade the product before customers notice them. One of the most critical things to monitor is whether the agent sticks to its assigned role. For example, a travel assistant should not start acting like a general concierge or skip approval steps. Changes in style, like becoming more verbose, often hint at deeper behavioral shifts. Also, output that looks valid but breaks semantic rules signals that the agent's decision-making is drifting from expectations. How the agent uses tools is especially important because actions define it more than words. A healthy assistant calls the right tool at the right time for the right reason. Sudden changes in tool calls can point to prompt problems, back-end failures, or brittle behavior when facing new phrasing. Tool failures and increased latency also show the agent might be struggling with its reasoning process. Some failures only appear inside the agent's internal process, not in its final answers. For example, it might produce a good summary while holding incorrect assumptions or leave behind fragile plans that break later. These internal issues are real product defects, and a lab helps reveal them by looking beyond the polished output. Observability for agents covers a broader range than traditional infrastructure monitoring because agents have complex behaviors tied to their runtime health. This part explains how to view an agent's actions and health as a unified picture. Agent observability goes beyond just server metrics. It combines familiar measures like latency and throughput with new dimensions unique to language model systems, such as how well the agent sticks to its role or chooses the right tools. Together, these form a comprehensive operational view. Traces play a central role because they record every decision and action the agent takes. They let teams understand why the agent followed a particular path, revealing steps like retrieving constraints, comparing options, or pausing for approval. Without traces, only the final result is visible, losing the reasoning behind it. Cost and token consumption are important signals because they often reflect how well the agent is performing. Excessive tokens might mean the agent is over-explaining or stuck in unstable control flow. Similarly, rising API costs or high latency can indicate inefficiencies or mismatches in back-end configurations, revealing deeper issues in the reasoning loop. Observing whether the agent follows its policy is crucial. This means checking if it respects approval steps, stays in the correct role, avoids forbidden actions, and formats outputs correctly. For example, a travel assistant must escalate booking high-value tickets properly. Even if the final response looks correct, the trace must show policy compliance to ensure trust. Treating observability signals as independent is a mistake. They often influence each other. A schema break might cause style changes, token spikes, and latency increases. Tool failures can lead to retries and user complaints. The observability surface connects these layers, making the agent's behavior inspectable in a way that reveals these relationships. Understanding the difference between development-grade and production-grade visibility is crucial. This distinction helps teams balance the need for detailed information with operational constraints and privacy concerns. In development, teams typically want to see everything. This means capturing every trace and inspecting every detail to understand how the system behaves. Since the user base is small and often internal, the costs and privacy risks of extensive logging are manageable. This approach is like leaving all the lab lights on to avoid missing any important signals. Production environments are very different. Capturing every detail at scale quickly becomes expensive and creates a lot of noise, making it harder to find useful information. There are also privacy and policy considerations that limit what can be recorded. Instead of trying to see everything, production visibility focuses on capturing the right data at the right level of detail to effectively monitor and respond to incidents. It's important to distinguish debugging from monitoring. Debugging needs very detailed information, but only for a short time, while monitoring requires a steady, sustainable flow of data over long periods. Although they can share tools and terminology, their default approaches to visibility should differ to meet their unique goals effectively. A mature production system designs its visibility to be elastic. When an incident occurs, the team can temporarily increase the amount of data captured to investigate the problem in detail. This flexibility avoids the extremes of either missing critical information or storing excessive data all the time. Planning for this adaptability from the start ensures effective incident response without overwhelming the system. Sampling in agent systems is not just a cost-saving compromise. It is a purposeful method for diagnosing system behavior. This approach helps focus attention where it matters most. Instead of treating sampling as a way to reduce data, it is better seen as a strategy to highlight important events. Errors are kept in full because they reveal rare but valuable insights. Successful runs, which are numerous and less informative, are sampled to manage resources without losing critical understanding. For example, a travel assistant should retain every run with errors like approval failures or malformed outputs, but sample successful itineraries at a rate that balances practical constraints. This rate changes depending on system state, higher during launches or changes, lower when stable, making sampling a flexible policy decision. Think of sampling as tuning a microscope. Routine activity is observed at low magnification to detect broad patterns, while failures or regressions trigger a higher zoom to capture detailed context. This adjustable approach is more effective than simply turning trace capture on or off. Capturing every successful interaction indefinitely leads to overwhelming data that is costly and hard to analyze. Sampling keeps the data manageable and ensures the team can focus on the most informative traces, making monitoring sustainable beyond initial deployment. Sampling rates should increase when problems arise, such as failures in a booking flow or changes in system behavior, allowing the team to investigate whether issues are isolated or widespread. Once resolved, the rate can decrease, making sampling an active part of engineering response rather than passive record keeping. This part explains why controlling sensitive data before it is stored is essential for responsible observability. We'll see how redaction and field filtering must happen during data capture, not afterward. Observability only remains responsible if it controls sensitive information before anything is permanently recorded. Redaction has to be built into the trace pipeline at capture time, not added as a cleanup later. Once personal or private data is logged, the risk is irreversible. So masking, excluding, or filtering fields must be mandatory steps before storing any data. Conversational agents like travel assistants receive highly sensitive inputs, passport names, travel dates, loyalty numbers, and more. While some data is needed for the system to work, not all of it should be stored in traces. Effective redaction must balance preserving useful debugging information with removing unnecessary personal data. The observability system needs to recognize the structure of a request, like a booking date or payment step, without storing every exact value. Techniques like masking partial values, truncating long inputs, or excluding entire sections help keep the diagnostic trail intact while protecting privacy. This approach treats privacy-preserving capture as part of instrumentation, not an afterthought. Teams often want to log everything to maximize debugging power, but in conversational systems, this can backfire. Rich traces contain sensitive details, which raises privacy, compliance, and cost concerns. The more data stored, the less willing organizations are to keep or use those logs. Redaction keeps observability practical and safe. Removing or normalizing sensitive values before storage forces teams to think about the overall structure of data rather than memorizing exact details. This shift helps debugging by focusing on whether the right categories of information flow through the system, making trace analysis more general, portable, and secure over time. Traces offer a detailed look into how a system behaves by recording its execution steps. Understanding these traces helps us diagnose why the system acted the way it did and identify points of failure or unexpected behavior. A trace is more than just a list of events. It serves as evidence that helps us form hypotheses about the system's behavior. Instead of simply admiring the sequence, we use traces to understand the root causes of failures, whether due to ambiguous prompts, incomplete retrievals, inconsistent tool data, or control flow issues. The most insightful traces make clear where decisions occur, such as planning, acting, observing results, or revising choices. For example, in a travel assistant, a trace might show how the agent adjusted its route after a fare change or missed an approval step due to a prompt alteration. These traces don't fix problems directly, but provide the clues needed to understand what went wrong. Traces can expose silent drift, where the system remains valid but changes behavior gradually, such as becoming more speculative or overusing tools. These subtle shifts often go unnoticed in normal use, but can predict bigger regressions. Detecting them early through trace reading helps teams intervene before users are affected. Comparing pairs of traces, one healthy and one degraded, highlights differences in actions and observations. This comparison accelerates understanding of what changed and why. The MVP lab collects these curated traces as behavioral specimens, making it easier to spot meaningful contrasts rather than sifting through random logs. This part explains how to use observations from agent traces to improve prompts, routing decisions, and tool integrations. Understanding this cycle helps turn raw data into actionable system improvements. Observability is useful only if it causes us to change something in the system. In agent products, the first reaction to trace data usually isn't swapping out the model. Instead, it often means tweaking prompts, adjusting routing, tightening schemas, revising fallback rules, or improving tool contracts. Treating the MVP as a diagnostic lab means using these findings to drive a disciplined improvement cycle rather than just reporting what happened. If a failure can be seen but not fixed, it's just a costly kind of ignorance. For example, a trace from the Atlas Travel Assistant might show that the planner keeps asking for the same missing detail because the prompt doesn't clearly state the missing information policy. Fixing this could mean improving the instruction hierarchy or adding a better state field for unresolved preferences. Another trace might reveal unnecessary use of a search tool when cache data already exists, suggesting a routing or retrieval improvement. Schema failures might indicate the need for stricter validation or clearer normalization before output reaches the user. This feedback loop is powerful because it grounds design decisions in real evidence rather than guesswork. Teams often rely on a few manual tests, but production traces expose where actual friction happens. A small wording change can reduce unnecessary tool calls. Better state representation can remove ambiguity that causes retries. A fallback rule can stop a small failure from ruining the user experience. The diagnostic lab turns these observations into testable engineering hypotheses. It's important to keep the improvement loop focused and narrow enough to learn from. Changing too many things at once makes it impossible to know which change caused the improvement. The MVP's value lies in enabling controlled iteration. Each trace acts like an experiment specimen, and every response should link back to a specific change. This approach turns observability into an active development method, not just passive reporting. Streaming emerges naturally when interactions take longer than a simple request-response cycle. This part explains why streaming is a key user experience feature for systems that need time to think, plan, or act. Many agents don't just respond instantly. They might think through problems, call external tools, or pause for approval, which makes the interaction last longer. Streaming shows users that the system is actively working during these steps, making the experience more transparent and engaging. When an interface waits silently for a full response, users might think it's frozen. Streaming can show progress updates or partial answers, helping users understand the system is working. For example, a travel assistant might say it's checking routes or booking hotels, which reassures the user that meaningful work is happening. Streaming makes the agent's ongoing activity and potential failures visible to users. This visibility pushes the product beyond just back-end concerns, encouraging designs that allow runs to be resumable and recoverable. The interface itself then admits the agent is doing real work, not just delivering static answers. This part explains how to build long-running AI agents that can handle interruptions and continue reliably. We'll cover key mechanisms like streaming outputs, saving checkpoints, pruning context, and using circuit breakers to manage execution safely. Instead of treating agents as simple request/response handlers, Think of them as workflows that can pause, resume, and recover. This model fits real-world scenarios where interruptions or delays happen during long tasks. Treating an agent like a conventional request handler works during early development, but fails when delays, approvals, or outages occur. Instead, view the agent as a live workflow that can be active, paused, checkpoint, resumed, or halted. This mindset is essential for production resilience. In the Atlas Travel Assistant, trip planning involves multiple steps and pauses for approval. If all these steps are hidden behind one blocking request, failures in any step look like system failures. Designing for continuation makes the interaction robust and user-friendly. Once agents call tools or wait for external input, every run needs a control model that tracks progress precisely. Without clear boundaries, restarting cleanly is difficult and trust in the system erodes. Resilience is foundational, not an afterthought. Think of streaming as live radar, checkpoints as landing pads, pruning as cargo repacking, and circuit breakers as safety triggers. These mechanisms don't make the agent smarter, but enable it to operate reliably and be managed as a stateful system. Focus on how streaming reveals ongoing progress to the client. Checkpoints save the current state for recovery. Pruning manages token limits by trimming context, and circuit breakers enforce limits to keep the system safe. Together, they form a resilient control loop. Streaming is the natural choice for long-running agent interactions. It keeps the user informed, reduces timeout issues, and supports intermediate events like tool calls or approval prompts, improving the overall experience. A streamed interaction shows progress as it happens, letting clients know the system is working. This contrasts with silent waits that feel like failures. Streaming creates a channel for partial results and interaction updates. Streaming doesn't change how the model reasons or plans. Instead, it reveals the run state in real time, enabling better operational decisions like continuing, canceling, or escalating based on live feedback. By streaming each phase, the client can render updates and the system can checkpoint after tool results. This avoids restarting entire runs or relying on inefficient polling, which is poorly suited for conversational workflows. The key operational benefit of streaming is making the workflow phase visible. This visibility allows the rest of the resilience mechanisms to function properly and ensures the system remains inspectable during autonomous decision-making. Defining what state must be preserved to resume or run is crucial. Not all text or data is equally important. Distinguishing execution state, transcript, checkpoints, and long-term memory helps avoid blurry implementations and ensures reliable recovery. Execution state drives the next steps, transcript logs dialogue, checkpoints capture safe snapshots, and durable memory stores long-term preferences. Keeping these categories distinct is key to clear, reliable system design. This state includes identifiers, model choice, system prompt, history slice, counters, costs, status, and halt reasons. It's not long-term memory, but the operational record needed to resume exactly where the run left off. History records messages and tool outputs, but can be pruned or summarized without breaking restartability, as long as essential execution facts remain in the state. Mixing transcript and state risks lossy restarts. A checkpoint is an execution artifact, not just a log. It must include lifecycle counters, status flags, and halt reasons so the system can restart without ambiguity or risk of repeating irreversible steps. Memory holds durable preferences or behaviors that persist beyond a single run. It should not be conflated with checkpoint state, which only restores the current workflow. Mixing them risks unintended profile changes on restart. Drawing a clear boundary around what must survive interruption simplifies testing and ensures faithful continuation. If you cannot restart the workflow correctly from a checkpoint, the boundary is too vague and the system unreliable. Notice how the recovery boundary encloses the serializable state and checkpoint, while transcript and long-term memory remain outside. This separation ensures the agent can resume reliably without conflating operational state with history or preferences. Checkpoint objects should be explicit, serializable, and compact. They form the contract between runtime and persistence, capturing exactly what must survive interruption without becoming an undifferentiated data dump. Its shape matters because it controls lifecycle visibility and recovery. It should include identifiers, model info, prompts, history, counters, status, halt reasons, and checkpoint counts to cover failure and recovery dimensions. The session ID links logs and storage. Model selection ensures resumed runs use the correct capabilities. Counters track usage and cost. Status and halt reasons inform orchestration. Checkpoint counts signal persistence events, aiding diagnostics. Messages record decisions, observations, and tool interactions. A consistent append method preserves structure for checkpointing and pruning. The summary method provides a concise inspection line for operators, showing status, turns, tokens, cost, and checkpoints. By consulting the session state, the runtime can decide to continue, checkpoint, or halt without reconstructing intent from logs. This reduces drift between execution and operator views and makes recovery a mechanical reload. This class defines the checkpointable session state. It includes identifiers, model info, system prompt, message history, counters for turns and tokens, accumulated cost, status, halt reason, and checkpoint count. The add_message method appends structured messages, while summary provides a concise status line for inspection. Checkpoints must be taken at safe stopping points to be useful. These include before irreversible actions, after tool calls, and at human approval gates. Proper timing ensures restarts don't cause ambiguity or repeated side effects. Before irreversible steps like bookings, checkpointing marks the last safe state. After tool calls, it records results to avoid repeats. At approval gates, it preserves authorization state, so pauses aren't treated as failures. Restarting doesn't continue the old process, but creates a new one using the checkpoint. This requires idempotent orchestration and no reliance on in-memory state. The checkpoint must survive crashes and redeployments cleanly. Checkpoints capture status, counters, and halt reasons so resumed runs know their exact phase. This makes interruption a planned state, not a memory failure, and defines what the system promises to preserve. This contract ensures the system can pause and resume safely, preserving workflow coherence. It is more valuable than any specific persistence technology because it makes interruption manageable and expected. Consider the Atlas Travel Assistant pausing at booking approval. A checkpoint then saves the itinerary, rationale, approval request, counters, and status. On restart, the agent resumes exactly where it left off without redoing prior steps. This snapshot preserves user intent and progress. If the process restarts, the assistant can continue the approval workflow without rerunning research or risking divergent results from repeated searches. Restoring the checkpoint avoids wasted cost and inconsistent results. The user expects approval to apply to the reviewed itinerary, not a regenerated one. This trust depends on accurate session state, including status and halt reasons. A raw transcript might show the assistant asked for approval, but won't reveal if the session is safe to continue or paused intentionally. This information is essential to avoid resuming the wrong path or duplicating side effects. Recomputing everything wastes resources and risks errors if external state changed. By restoring the last safe checkpoint, the system makes fresh decisions from a known baseline, preserving continuity in a changing world. This code manages checkpoint persistence. Save_checkpoint writes the session state to a JSON file, incrementing a counter on success. Load_checkpoint reads and validates the save state for resuming. List_checkpoints returns all saved session IDs. This simple file-based approach illustrates checkpoint mechanics. Checkpointing solves recovery, but not token limits. The context janitor prunes history selectively to keep the context window manageable without losing the conversation's operational meaning. The janitor isn't a long-term memory manager, but a short-term strategy to keep the next model call within token budget while preserving key assumptions and recent context. The system prompt contains the agent's operating rules and must be kept. Recent turns capture fresh context. The middle, often older and less critical, can be summarized or compressed to reduce token usage without losing essential information. Instead of deleting the middle outright, the janitor creates a compact summary indicating how many messages were pruned and which roles dominated that section. This keeps the model aware that context was compressed intentionally. This targeted approach keeps trip preferences, recent decisions, and approval states intact while compressing older search iterations. It balances token efficiency with workflow coherence, enabling the agent to keep its place without growing context indefinitely. Naive truncation risks removing system prompts or unresolved tool outputs, breaking the run's logic. Pruning that respects role, recency, and boundaries keeps the run viable even as it grows beyond the context window's comfortable size. This function prunes conversation history to fit within a token budget. It preserves the system message and recent turns, then summarizes the middle segment with a synthetic system message describing the roles and count of prune messages. This keeps the context coherent and manageable. Understanding pruning requires distinguishing it from truncation and summarization. Each has benefits and risks, and choosing the right approach affects system reliability and correctness. Simply cutting off older messages can lose key decisions or approvals. For example, losing a user's approval request might cause the agent to proceed incorrectly, producing confident but unsafe behavior. Good summaries keep runs coherent, but bad ones blur unresolved questions or erase decision origins. Summarization changes information structure and must be deliberate and tested to avoid failures. It keeps important anchors and recent dialogue while replacing older content with summaries. Tool outputs often justify next actions, so pruning must retain their essence to avoid repeated lookups or incorrect inferences. These errors weaken agent behavior contracts and risk unsafe actions. A healthy pruning strategy preserves rules, recent commitments, and only compresses older supporting material, keeping risk visible rather than hidden. Long-running agents need explicit limits to avoid runaway costs or endless loops. Circuit breakers monitor spend and turn count, bounding the workflow's behavior envelope and enabling safe, autonomous operation. A run might be cheap, but stuck in a loop, or expensive without looping. Both cost and loop limits are necessary to prevent economic or operational failures and keep the agent's autonomy bounded. They aren't emergency afterthoughts, but policy enforcers. In Atlas, repeated cheap searches or a single expensive booking can both trigger a halt. The system must stop even if the model wants to continue. This order ensures the orchestration layer can inspect why the halt occurred without relying on stack traces. A domain-specific exception and updated session state make the stop graceful and actionable. A halted session isn't broken. It has reached a configured limit. This distinction improves user experience and operator response, signaling correct behavior within policy, even if the user prefers otherwise. The runtime compares totals to caps, marks status as halted, records halt reasons, and raises exceptions the orchestration layer can catch. This makes halts manageable, allowing logging, user messaging, or later resumption. This code defines a custom exception for circuit breaker trips and a function to check budget and turn limits. If limits are exceeded, it updates session status and halt reason, then raises the exception to stop execution cleanly. These resilience mechanisms become effective when integrated into a single control loop. The loop streams progress, updates state, checkpoints safely, prunes context, and checks limits before continuing or halting. Taking checkpoints too late or pruning too early can cause failures. Checking circuit breakers infrequently risks runaway costs. The loop defines explicit decision points to preserve what matters and stop what shouldn't continue. It streams flight comparisons, checkpoints after itinerary selection, prunes old search turns, and stops at risky bookings. On crash, it reloads checkpoints to resume safely. Turn and token limits prevent billable loops and context overflow. Streaming keeps the interaction visible. Checkpoints make the workflow restorable. Pruning manages context size. Circuit breaker bund autonomie. Together, these mechanisms create a robust operational envelope for production agents. These four mechanisms address different failure modes and work together to keep long-running agents reliable. They allow workflows to pause, resume, recover from crashes, and stop safely without losing progress or exceeding limits. This part explains why simply parsing output correctly is not enough for a production agent. We'll explore the deeper requirements needed to ensure the output is truly reliable and actionable. Parsing success just confirms that the output is syntactically valid, like well-formed JSON. But this is the weakest signal because it doesn't tell us if the output is safe to route, store, or act on. We need to look beyond parsing to whether the output meets the full application contract, which involves 3 layers: syntax validity, schema conformance, and semantic stability. Consider a support ticket example where the agent extracts fields like ticket ID, priority, and customer sentiment. If the priority is wrong, a critical incident might be delayed. If categories are swapped, the wrong team gets assigned. If sentiment is misread, escalation rules might not trigger. This shows that output is not just data formatting, but a decision input with real operational consequences. The best approach treats the model's output as a contract boundary, assuming failures can happen at different layers. Strict decoding on the provider side ensures shape correctness early. Client-side validation lets you handle errors and retries in your own process. Degraded recovery allows the system to continue operating in a reduced capacity if other layers fail. These layers work together to maintain confidence in the output. This diagram illustrates the 3 layers a structured output pipeline must pass. Syntax checks ensure the output is well-formed, schema checks verify the fields and types, and semantic checks confirm the meaning is stable enough for reliable downstream use. This figure shows how reliability depends on multiple layers working together. Each layer defends against different failure types, and degraded recovery acts as a fallback to keep the system running, even if some checks fail. Focusing on contract success shifts attention from just reading or validating output to trusting it for the actions it triggers. Semantic stability is crucial because if labels or values drift, the system's behavior changes. True success means the output preserves the intended product behavior across runs and versions. Structured output can fail in many ways once it moves beyond demos into real-world applications. Understanding these failure modes helps us design better systems that handle errors gracefully and maintain reliability. Malformed JSON, like an unclosed object or stray text, is straightforward to catch because it breaks parsing. However, outputs that are valid JSON but miss required fields or that convey incorrect meanings pose bigger risks. These cases need different handling, such as flagging uncertainty or escalating issues instead of just retrying. When a model outputs labels outside the accepted set, like urgent instead of P0 for priority, it creates enum drift. This can silently break routing or analytics if the system only checks for presence, not validity. Enforcing strict type and enumeration checks is essential to prevent these subtle but impactful errors. In pipelines where structured data passes through multiple steps, the meaning of fields can shift even if the JSON remains valid. For example, an extracted field might be accurate initially but lost or reinterpreted later. This makes reliability a pipeline-wide concern, not just a single call issue, because errors can accumulate invisibly. Different models or providers may interpret labels differently while still producing schema-valid output. This semantic inconsistency can pass smoke tests unnoticed but cause business regressions later. Understanding that structure includes meaning as well as format helps us address these compatibility challenges effectively. Provider-enforced strict schema decoding means the model generates output that must match a predefined JSON schema exactly. This approach ensures the data structure is correct right from the start, which is crucial for reliable downstream processing. This method asks the model to produce output that fits a declared JSON schema as it generates the response, rather than letting it produce free-form text and fixing it later. This reduces the chance of formatting mistakes and makes the first response more likely to be usable without extra cleanup. When you send a strict schema request, you specify exactly which fields are allowed, which are required, and what values they can take. The model then generates output that must follow these rules, effectively moving some validation into the generation step itself. This reduces malformed outputs and the need for retries. Strict schema decoding guarantees that each generated output fits the schema, but it doesn't ensure that the meaning behind the data stays consistent over time. For example, the model might assign different priority levels to the same input in different runs, which is a product-level variation, not a schema violation. Strict decoding works best when the schema is very precise, with enumerations and required fields that limit how much the model can vary its output. But even a tight schema only controls what you specify. It can't prevent the model from choosing different valid outputs when the task is ambiguous. So, strict decoding is a strong first defense, but not a complete solution. Strict JSON validation ensures data follows a schema, but it doesn't solve every problem. This part explores where relying solely on strict JSON falls short in real workflows and system interactions. When one tool produces a clean JSON object and passes it to another, each handoff risks changing the meaning. For example, an initial extraction might capture a customer's anger about a failed login reset, but a later summary could reduce it to just a generic login issue. Even though the JSON remains valid, the original detail can get lost. In workflows with multiple steps, each completion can produce valid JSON, but still shift the meaning slightly. For instance, summarizing a ticket, deciding urgency, and drafting a response might each introduce subtle changes in labels or emphasis. Downstream logic often assumes earlier outputs stay stable, but without validation and normalization at every step, the meaning can drift. The path JSON takes through proxies, gateways, and streaming layers can modify headers or content fragments. These changes might not break JSON validity, but can cause corner cases to behave differently in production. That's why relying solely on provider guarantees isn't enough. The application itself must enforce validation where it has full control. Two models can both produce valid JSON that fits the same schema, yet differ in label choices, ordering, or inferred priorities. This means strict JSON validation alone can't catch behavioral changes after a model upgrade. To maintain consistent behavior, strict JSON must be combined with local validation, canonicalization, and reference tests. This tier focuses on validating data on the client side using typed models and managing retries when validation fails. It ensures the application enforces its own data contracts and handles errors intelligently. Client-side type validation turns a loosely generated object into a strict contract by verifying its structure and content inside the application. For example, a Pydantic model can decide if a support ticket is valid or needs correction. This boundary is explicit and local, so the application doesn't rely on the provider's decoding behavior to catch missing or malformed fields. Instead, it enforces rules that can be versioned and tested like any other business logic. The validator layer distinguishes between failures that can be retried and those that cannot. Transient transport errors like server timeouts should trigger retries because the request might be fine. Validation failures, such as invalid data formats, might be recoverable by retrying with a stronger prompt or stricter validation. However, persistent schema mismatches indicate deeper issues and should not be retried indefinitely, as that wastes time and hides the real problem. The retry policy must understand these failure types. Using typed wrappers, such as instructor combined with Pydantic, lets the model produce structured objects that are parsed and validated against the application's contract. If validation fails, the wrapper can retry a limited number of times before giving up. This retry loop is crucial because it connects the provider's output guarantees with the application's need for reliable, valid data. Only the validator can confirm if the output meets the business rules, even if the provider claims the output is valid JSON. Not all normalization is equal. Some fields, like category labels, can be mapped conservatively without losing meaning. Priority fields accept a range of human terms and reduce them to standard levels. Sentiment can be normalized more aggressively since only broad categories matter. But when a field cannot be confidently mapped, the validator should fail clearly or revert to a marked default. Validation is about preserving contracts, not inventing data. Observability is critical here. When validation triggers a retry, the system should record both the failure and the recovery path. If the system falls back to a conservative default, that signals reduced confidence in the product's behavior. Client-side enforcement not only ensures correctness, but also generates data about how often the model meets the contract, requires normalization, or drifts away from expected behavior. This code defines normalization maps for categories, priorities, and sentiments, mapping various input strings to canonical values. The support ticket class uses these maps and field validators to enforce consistent, normalized data before validation. If a priority value cannot be mapped, it raises an explicit error, preventing silent failures. This approach creates a stable interface for downstream systems relying on standardized labels. These normalization maps are not just helpers. They form a compatibility layer owned by the application. They allow the model to express concepts in varied ways while the system maintains a stable vocabulary. This stability is essential because downstream components like routers or dashboards depend on consistent labels rather than raw model outputs. The normalization maps become part of the product interface, ensuring reliable communication across the system. The instructor client enforces this boundary from the generation side by invoking typed response models with built-in validation and retries. Without this wrapper, the model might produce loosely structured text that requires manual cleanup. With it, the output is validated as part of the request, enabling the system to differentiate between transport errors, validation failures, and true successes. This integration is key to reliable application behavior. This code sets up an instructor client configured for JSON mode, wrapping an OpenAI-compatible endpoint. The call_openRouter function implements a retry loop for transient server errors between retries. It waits briefly with jitter to reduce load. Client errors immediately raise exceptions. This retry mechanism handles transport failures separately from validation, ensuring the system recovers from temporary outages without masking deeper issues. Transport retries address transient network or server errors, while validation retries focus on semantic correctness. Mixing these can cause indiscriminate retries that hide model problems. In production, these failure types should emit separate signals, use different backoff strategies, and appear in distinct dashboards. This separation prevents masking systematic issues behind normal network noise and improves operational clarity. This tier focuses on maintaining system continuity when all other validation methods fail. It uses degraded prompts to coax minimal, usable JSON responses as a last resort. When strict validation by the provider and client side checks both fail, degraded recovery steps in. It tries to get a minimal JSON response by guiding the model with a simplified prompt. But this approach is inherently weaker because it depends on the model following instructions instead of enforced rules. This mode should be treated as low confidence and flagged accordingly. The main goal here is to avoid stalling business processes. Even if some fields like priority can't be fully validated, getting a summary or ticket ID can still be useful. However, the system must never treat these degraded results as fully reliable. It should record that a fallback was used and keep traceability so operators know the data's confidence level. To maximize what can be salvaged, degraded prompts must be very focused. They ask for a simple JSON object with a fixed set of keys and predefined values, forbidding additional text. This doesn't guarantee full correctness, but it helps preserve enough structure for downstream workflows to proceed carefully, routing tickets appropriately even if some fields remain uncertain. It's important to apply conservative defaults carefully. They should only be used when they maintain safe behavior and are clearly marked in the system's trace logs. The system should never pretend it knows a precise value if the input doesn't support that confidence. Instead, it should emit a conservative label, mark the data as degraded, and make uncertainty observable to avoid false confidence in production. Normalization maps act as the semantic stabilizers in a structured output pipeline. They ensure consistent meaning despite changes in wording or model versions, protecting the system from unpredictable variations. Normalization maps don't fix broken generation or replace validation. Instead, they handle variations in wording by translating different inputs into a stable internal language. Think of it like an API shim that lets older or varied inputs work with a consistent backend format. The model's output can change, but the normalization map keeps the internal representation steady. Consider support ticket categories like authentication, login, or sign-in issues. They often mean the same thing operationally. If routing expects a single label like login, preserving multiple aliases only complicates analytics and queue management. Normalization maps merge these synonyms into one control vocabulary, enforcing a semantic contract rather than just cleaning data. The key design principle is conservatism. Normalization should combine obvious synonyms, but not guess when input is unclear. For ambiguous labels, it's safer to assign a broad category like Other and flag it for review. Similarly, unclear sentiment should default to neutral rather than forcing a strong emotion. This approach reduces variance without inventing meaning, preventing normalization itself from causing drift. Canonicalization helps maintain stability even as prompts or models evolve. Without it, any wording change can ripple through routing, analytics, and alerts. With canonicalization, the model's language can flex while the application's internal contract stays fixed. This reduces brittleness and creates a clear boundary for testing, allowing the model to evolve without accidentally changing product behavior. Think of normalization as a pipeline from raw label to canonical label to business action. The raw label is what the model outputs. The canonical label is the stable internal meaning. The business action is what the system does based on that meaning. Only the normalization layer should change internally. If business actions shift because canonical labels change, normalization has failed. If actions stay consistent despite raw label variation, normalization has succeeded. Semantic drift occurs when outputs remain syntactically correct but change their intended meaning or business logic. Understanding this difference helps us catch errors that look like success but cause operational problems. Semantic drift is tricky because the response can parse correctly and meet schema requirements, yet still represent a different business decision each time. This hidden shift can disrupt processes like routing and escalation, even though the syntax looks fine. We can think of syntactic success as simply parsing and structural validation, while semantic validity ensures the output aligns with the business rules. Many teams focus only on syntax because it's easier to measure, but that can mask serious issues in decision-making logic. A practical way to check semantic validity is with a checklist. The category should accurately reflect the issue. Priority must match urgency cues. Sentiment should reflect customer tone, and suggested actions must be consistent with category and priority. This goes beyond schema checks to ensure operational sense. When models change, They might keep the JSON structure intact, but shift how they prioritize or classify inputs. Testing only syntax misses these changes, while decision-level checks reveal them as regressions. This approach ensures the output still delivers the intended message, not just a well-formed envelope. Schema insurance ensures that when we replace models, the system continues to behave as expected. This approach treats model updates as serious integration changes, not just simple tweaks, helping maintain consistent application behavior. Model replacements occur often for various reasons like reducing costs, improving latency, switching providers, or evolving capabilities. These changes can alter the distribution of structured outputs, which impacts how the system interprets data. The key is to test not only whether the data structure remains valid, but also whether the fallback and normalization processes preserve the intended business logic. Small changes can reroute tickets or alter priorities, which can have costly consequences. Regression testing should be guided by the application's contract. Differences in priority or label usage that affect outcomes are regressions, even if the schema is valid. The tests need to separate acceptable changes from those that degrade system behavior. Monitoring for increases in fallback usage or shifts in category distributions helps detect when a structured output contract is under pressure. Such alerts indicate that a model update needs careful review to prevent unexpected production issues. This walkthrough covers the full process of handling a support ticket from initial extraction to final canonicalization. Understanding these steps clarifies how we ensure data accuracy and operational reliability in automated support systems. The first step is to extract information from the customer's message using a strict schema enforced by the provider. This ensures the output matches the expected structure and keys of the support ticket object. While this guarantees syntactic correctness, it doesn't ensure the model's categorization or priority assignment aligns with the actual urgency or issue type. After extraction, client-side validation checks the data against a typed contract using tools like Pydantic. This step normalizes categories and priorities to business standards, such as mapping various login-related terms to a single category or converting priority labels into canonical forms. It also rejects or retries malformed data, ensuring the system only accepts valid, actionable information. If validation still fails, the system uses a degraded prompt path as a fallback. This path produces a minimal JSON object that keeps essential information like the login category and urgency. Although weaker in guarantees, this approach maintains workflow continuity and marks the output as degraded so downstream processes handle it cautiously rather than assuming full reliability. The final step is canonicalization, which converts whatever valid object remains into stable values for category, priority, and sentiment. This ensures that the rest of the system can route and summarize tickets consistently, regardless of which model produced the data or which synonyms were used. It preserves the contract, makes uncertainty visible, and keeps the output useful even if earlier enforcement was imperfect. Maintaining explicit confidence boundaries between extraction, validation, and canonicalization is crucial. Each stage represents a different level of guarantee, and making these distinctions clear in code and logs helps build trust in the system. Without this transparency, structured output can create a false sense of safety. Production systems need honest guarantees, not hidden assumptions. This part explores the important difference between simply parsing a model's output and truly trusting it to make decisions. Understanding this gap helps prevent errors that come from relying on well-formed but potentially misleading data. Even if a model's output fits every required format and passes all schema checks, that doesn't guarantee it's the right answer. The output might still lead the system down an incorrect path, such as triggering wrong approvals or actions. This is why outputs should be treated as proposals to review, not commands to execute blindly. When a model produces malformed JSON, the error is obvious and immediate. But when it outputs valid JSON that subtly changes meaning, the system often continues without noticing. This creates a false sense of stability, where dashboards look fine, but user experiences shift unexpectedly. This risk is greater when outputs drive decisions or trigger actions, since small changes in meaning become big changes in execution. It helps to think of three separate questions. Can the output be parsed? Does it mean what you expect? Is it safe to act on? A response can be parsable but unstable in meaning. It can seem reasonable but be unsafe due to low confidence or missing context. and it can be consistent individually but inconsistent across runs, making the system unpredictable and harder to maintain. This figure highlights that while structure output makes the response readable by machines, the decision to act depends on deeper checks. Semantic validation ensures the meaning aligns with expectations, and safety validation confirms it's appropriate to proceed. In real systems, there needs to be a clear boundary where output is validated beyond just structure before any action happens. This gate includes explicit checks and fallback logic to catch semantic shifts or inconsistencies. Without it, you only verify the envelope, not the message, risking unstable decisions over time. This diagram shows how a production system isolates generation from execution. The validation boundary acts as a checkpoint to confirm outputs are trustworthy before triggering actions. If validation fails, the fallback path ensures safe handling without unintended consequences. Semantic drift occurs when a model's outputs shift in meaning or label choice across repeated runs on the same task. Understanding this helps us see how such changes impact real-world deployments, where consistency matters more than occasional correctness. Semantic drift means the model might give different answers each time it runs on the same input. The issue isn't whether the answers make sense individually, but whether the model is consistent enough to keep downstream systems predictable. Even if both answers are valid, switching between them can cause problems because the decision boundary moves while the output format stays the same. This matters in deployment because repeated runs are expected to behave the same way. For example, a support ticket might be labeled urgent one time and moderate the next. Or a travel assistant might flip between marking a trip as research only or ready for booking. The model isn't necessarily broken. It might just be sensitive to subtle changes in prompts or context. But from the product's view, this unpredictability is a problem. Drift doesn't only mean flipping labels completely. It can be smaller shifts, like changing urgency levels or nudging reviewers with different justification texts. These subtle changes affect decisions like whether to escalate or automate a task. In agent systems, these policy shifts carry real operational weight because they determine what happens next. The key point is that drift means inconsistent decisions on the same input, not just grammatical errors. Even if every response looks valid, if the model's outputs differ in meaningful ways across runs, that's a reliability problem. Deployment teams must focus on decision consistency. Stable output formats let code parse results, but stable meaning lets code trust those results. Without both, the system may seem deterministic but behave unpredictably. Small changes in classification labels can lead to big impacts on how systems behave and respond. This part explores why even a tiny label flip matters a lot in real-world operations. Imagine a support agent labeling cases as P0 for urgent escalation or P1 for regular processing. If the model returns P0, it triggers immediate action. If it returns P1 for the same case, the issue waits in the normal queue. Both labels are valid alone, but they cause very different outcomes. Labels don't just describe situations. They control what happens next. A P0 label might bypass queues or override service rules, while P1 delays attention. If the label changes without a real situation change, the system acts inconsistently, causing serious issues that look like classification errors but are really operational failures. When a model produces a wrong label confidently and neatly, it can fool teams into thinking everything is fine. Broken outputs trigger alarms and investigations, but polished wrong answers invite complacency. This makes subtle errors especially risky because they hide in plain sight. Stability means consistent decisions across repeated, identical inputs. A single run might look stable, but small changes can flip decisions near boundaries. This hidden instability causes inconsistent escalations and approvals. The real issue is treating a probabilistic model like a fixed rule, which it isn't. Structured output is an important first step in ensuring safe and reliable model behavior, but it alone cannot guarantee correctness or appropriateness. This part explains why schema compliance is necessary but not sufficient for safety. Structured output converts a model's open-ended response into a precise format that machines can reliably interpret. This makes it easier to validate and handle downstream. However, just matching the schema doesn't guarantee the output is factually correct, aligns with policy, or is operationally sound. The content inside that valid structure can still be wrong or misleading. Think of validation as climbing a staircase rather than passing through a gate. The first step checks whether the output is structurally correct, which is easy to automate and measure. The next step verifies if the content makes sense for the task or business rules. Finally, execution applies the output to real-world actions. Many teams stop after the first step, but that alone doesn't prove the output is safe or correct. Semantic validation is more complex because it depends on the specific task. It might check if a label fits allowed values, if a decision follows policy thresholds, or if recommendations respect constraints. It can also compare outputs against user intent or recent context. This step asks not just if the format is right, but if the answer should influence what happens next. Some teams mistake high schema validation rates for overall quality because it's easy to measure. This creates a measurement trap. The metric that's easy to collect isn't the one that truly matters. Format correctness is necessary infrastructure, but it can't replace the need for correct, reliable decisions in agent systems. Instability in model outputs can create real risks for products. This part explains how unpredictable behavior in models translates into operational and governance challenges that affect the overall system. When a model's meaning shifts over time, it risks misclassifying requests. For example, if urgent requests are labeled routine, the organization misses critical intervention windows. Conversely, labeling routine cases as urgent wastes attention and creates operational debt. Both issues stem from the model becoming an unreliable judge of important decision boundaries. Imagine a travel assistant that sometimes asks for approval on the same itinerary and sometimes doesn't. This inconsistency breaks the approval gate's role as a dependable control. It's not just a user experience problem. It undermines human ability to supervise because the system can't consistently flag when oversight is needed. The control process becomes unstable and ineffective. Automation that relies on model outputs to route or approve work inherits the model's instability. It may perform well in demos with narrow test cases, but in real-world use, varied language and edge cases cause unpredictable errors. Early incidents might seem like flukes, but over time, this instability erodes trust and operators stop relying on the system. When reviewers see outputs flip unpredictably, they compensate by adding manual checks, which slows processes and negates automation benefits. The system still produces valid results, but the organization quietly reintroduces manual oversight everywhere. This means the deployment hasn't failed technically, but it has failed economically by losing efficiency and increasing costs. Validation boundaries define where a model's output is checked before it triggers any action. This concept is crucial to ensure that decisions made by AI systems are safe and reliable. When a model produces unstable or uncertain results, the solution isn't to trust it more blindly. Instead, the system should clearly mark where the model's output ends and where the system decides whether to act on it. This validation boundary comes after parsing the output into a structured form, but before any irreversible action, to prevent questionable decisions from affecting the real world. At this boundary, the system stops treating the model's output as final. Instead, it becomes a candidate that must pass checks like allowed values, confidence levels, or business rules. This means the model is just one input among many, not the ultimate authority. The system only acts when the output meets all these criteria, ensuring that a syntactically correct answer isn't blindly executed. Without a validation boundary, failures can be hard to diagnose because they mix issues from the model, the schema, and the business logic. With this boundary, the system can log whether a failure happened during parsing, validation, or execution. This clarity helps teams know whether to adjust prompts, tighten policies, or fix schemas, preventing wasted effort on the wrong problem. For actions with high risk, the system should default to stopping or requesting review if the model output is uncertain. The goal is not to maximize automatic actions, but to ensure the model's output is reliable enough before proceeding. This approach distinguishes a responsible agent from a hopeful script by prioritizing safety and correctness over speed. Fallbacks provide alternative actions when a model's decision is uncertain or unreliable. They help maintain safety and reliability by offering a plan B when the primary output can't be trusted. Validation tells us when to stop and flags problematic outputs, but it doesn't say what to do next. Fallback logic steps in to handle these cases by deferring to humans, switching to simpler rules, or asking for clarification. The choice depends on how risky the action is. Retries assume the problem is temporary, like formatting glitches, and that another attempt might fix it. Fallback assumes the issue is deeper. The output might look fine but still be unreliable. Repeating the same call often just repeats the uncertainty, so fallback provides a safer alternative path instead of just trying again. For example, a travel agent might hold off on booking until a human reviews uncertain itineraries. A support system might escalate unclear priority cases to specialists. These fallbacks stop the system from acting on uncertain information as if it were certain, which is crucial since uncertainty affects real operations. Relying solely on complex validators can make a system fragile and hard to update. Fallback acts as a release valve, keeping the system safe even when the model isn't perfect. The goal isn't to remove all uncertainty, but to handle it so the system can operate reliably. This part focuses on why evaluation must go beyond checking if a model produces the right answer once. It highlights the need to ensure the model's decisions remain stable and consistent over time in different conditions. Semantic drift introduces a risk that a model's behavior changes unexpectedly after deployment. So, evaluation can't just verify a single correct output. Instead, it must confirm that the model consistently makes the same decision across different prompts, versions, and environments. Many teams mistake passing a few tests for success, but a model can still be unstable if small changes to input wording or order cause different outputs. The key is to check if inputs that mean the same thing lead to the same decisions every time. Updates like new prompts or model versions can subtly change how decisions are made, even without code changes. Simply checking if outputs parse correctly won't catch these shifts. Instead, evaluation should confirm that the system's decisions remain consistent after every change. Semantic drift isn't just a minor issue. It signals that the model's behavior can change unpredictably with updates. Evaluation acts as a safeguard, making these changes visible early so deployments don't silently shift while everyone assumes the system is stable. This part explores how the challenges of semantic stability relate directly to the realities of serving AI models in production. Understanding this connection is crucial for maintaining consistent and trustworthy outputs. Semantic stability isn't just about the model itself. It also depends heavily on the environment where the model runs. Factors like the backend system, inference server, cache layers, and deployment setup all influence output consistency. Even if the input prompt is the same, outputs can vary due to differences in load, warm-up state, or memory pressure during serving. Infrastructure doesn't cause all instability, but it can make hidden issues more visible or hide problems that would otherwise appear. A deployment that seems stable on one backend might behave differently on another. Similarly, a system reliable at low traffic may become inconsistent under bursts. These serving factors directly affect how much you can trust your model's output. Operational consistency comes from a combination of the model's behavior, validation limits, fallback mechanisms, and the physical realities of how inference is served. Product teams often misjudge instability by blaming prompts too much or ignoring deployment effects. Knowing the serving physics helps you select backends and configurations that preserve the critical decision properties your system depends on. Serving a model on your own infrastructure requires understanding the underlying system behavior, not just the model's outputs. This part explores how serving physics shapes user experience when hosting inference yourself. We move beyond treating inference as a simple API call. Instead, we examine the physical realities of serving. Startup times, memory use, request scheduling, and caching all impact how responsive the system feels. When deploying an agent against a self-hosted model, inference is not just a generic endpoint. It's a runtime environment with measurable serving physics. The startup path, memory residency, request scheduling, and cache behavior all influence the user's experience. For example, two backends might produce the same answer, but one feels snappy while the other feels slow or inconsistent. This difference comes from the serving system, not the model's intelligence. The most useful metrics to understand serving performance are straightforward. Time to first token measures how long the user waits before the model starts responding. Warm request latency captures the speed once the system is ready. Throughput shows how much work the server can handle concurrently. Tail latency reveals slow requests that users often notice. A system can have good average latency, but still feel slow if tail latency or cold starts cause delays. This figure highlights 4 core metrics that describe serving performance. Time to first token shows initial responsiveness. Warm request latency reflects steady-state speed. Throughput measures capacity under load. Tail latency captures the worst-case delays users experience. Together, they provide a comprehensive picture of how the system feels in practice. Atlas Travel Assistant's workload is complex. It's conversational, with varying turn lengths, shared instructions, and branching tool use. Sometimes the workload is prefix-heavy, repeating long instructions. Other times it branches into multiple plans. Traffic can also be bursty, with clustered users. Each pattern stresses different parts of the serving system. A backend optimized for one shape may struggle with another, so deployment must consider these workload characteristics. It's helpful to think of the model and server as distinct. The model is the learned function, like a skilled chef. The server is the kitchen with its tools and resources. How efficiently the kitchen operates, its prep speed, workspace, and order routing determines how quickly meals reach the table. Similarly, serving efficiency depends on what can be reused, recomputed, or shared. This is why backend choice must be informed by workload, not just brand or hype. Cold start is a fundamental operational event, not a rare exception. It represents the time and resources needed to bring a model from storage into a ready state to serve requests. Understanding cold start is crucial for realistic performance expectations. Cold start involves several steps: locating and reading model weights from storage, loading them into GPU memory, initializing backend data structures, and warming the runtime so the first token can be generated. Each step adds latency before the user sees any output. This startup cost can be much larger than the latency of steady-state requests. The first request, after scaling up or restarting the service, feels slower because the system performs initialization work not required by later requests. The model itself hasn't slowed down. This distinction matters because a backend with great warm latency can still deliver a poor user experience if cold starts are frequent. Measuring cold start penalty is essential. Knowing a backend starts in about a minute isn't enough. You must understand how startup time interacts with traffic patterns, auto-scaling policies, and how long users will wait. For example, a model that responds quickly when warm may still feel unusable if the first response after idle takes tens of seconds. Cold start must be planned for and measured. If instant responsiveness is critical, the serving system should maintain always-on capacity or aggressively pre-warm workers. Alternatively, the user experience can mask delays with asynchronous processing or status updates. Assuming a fast model automatically means a fast product ignores the startup costs that users often experience. Scale to zero saves money by shutting down idle workers, but it shifts costs from infrastructure to user experience. Understanding this trade-off is key to balancing cost and responsiveness. Scaling workers down to zero cuts idle GPU costs, which can be significant. However, this saving comes at the expense of increased latency for the next user, who must wait through the startup path. Essentially, idle cost is converted into a startup delay charged against user patience. Whether scale to zero works depends on traffic patterns. For rarely used overnight services, startup delays may be tolerable. But for consumer apps with sporadic, latency-sensitive requests, even a few seconds delay can feel broken. Bursty traffic worsens this inconsistency, making some users wait while others get instant responses. Scale to zero should be seen as a policy choice balancing responsiveness against cost. Latency-sensitive workloads may need warm replicas despite higher cost. Batch or asynchronous workloads may benefit from aggressive scale down. The key is modeling service behavior based on real user patterns, not just utilization metrics. Atlas's usage pattern is conversational but intermittent. Users may pause and return later, causing repeated warm-up phases if scaled to zero is aggressive. Keeping the service warm improves responsiveness but costs more. The best choice depends on user expectations, request frequency, and delay tolerance. Managing cold start effectively requires a well-designed restart path and persistent storage of model weights. This ensures quick recovery and reduces startup delays. Treating model weights as ephemeral assets is a common mistake. In production, weights must reside in durable storage with predictable access. Restart procedures should load weights from local or mounted volumes quickly, avoiding repeated downloads. This persistence is essential for feasible scale-up times. Storage affects serving speed beyond durability. If checkpoints are on remote or poorly provisioned storage, startup slows. Misconfigured permissions can cause failures before loading. Locality and repeatability of storage access are crucial to minimize cold start overhead. Persistent waits belong to the deployment artifact and survive restarts. Runtime state, such as KV caches or active requests, is transient and lost on restart unless explicitly checkpoint. This distinction clarifies that durable storage does not imply the agent remembers past conversations, only that it can restart without reloading the model from scratch. For Atlas, the restart path must allow a new worker to mount and load weights quickly with minimal manual intervention. Fragile storage or loading processes risk availability. Persistent storage not only protects data, but ensures the service recovers fast enough to avoid downtime noticeable to users. Once the model is warm, the KV cache is the main optimization. It stores intermediate representations from prompt tokens to avoid recomputing them during generation. This cache is crucial because processing long prompts or histories is costly. During prompt prefill, the backend computes and caches attention keys and values for input tokens. This cache lets the model reuse computations for each generated token, saving time especially when prompts include long instructions, policy text, or conversation history. If Atlas receives a fresh request with a long shared prefix, the server must pre-fill that context before generating tokens. Later turns sharing the same prefix can reuse the cache computations, moving faster into decoding. This is like a kitchen that has prepped ingredients in advance, speeding meal assembly. Every additional token in context increases memory usage for active requests. This memory competes with concurrency and batch size. If too many long contexts run simultaneously, the server may spend more time managing memory than producing tokens, reducing efficiency. Serving speed depends on memory availability. A request may be slow not because the model is weak, but because the server cannot hold enough computation and cache state simultaneously. Agent workloads are harder than simple chat because they accumulate state and branch, increasing token footprint and memory use. The KV cache exists only to speed the current or closely related serving sessions. It disappears on process restart or when the request changes enough to invalidate the prefix. This makes it a performance tool, not a persistence mechanism, which is important to avoid confusion in agent system design. Prefix caching allows reuse of cache computations for shared prompt prefixes across requests, but has limitations. Understanding these failure modes is critical for optimizing serving performance in agent systems. When many turns share the same policy text or instructions, prefix caching lets the server skip recomputing those parts. This lowers average latency and improves time to first token by reaching generation faster. Prefix caching matches exact or nearly exact prefixes. Reordering sections, adding sentences, or changing tokens can break reuse. This recipe mismatch problem means prompt stability is an operational concern, not just a prompt engineering preference. If the agent explores alternative plans or frequently rewrites instructions, caching benefits shrink. Branching conversations may look like a single chat externally, but if each branch changes early tokens, the backend must recompute prefixes repeatedly, increasing latency. Stable system prefixes and consistent formatting improve cache reuse, but this is not a universal fix. If workloads naturally diverge, reuse will be limited. The serving system must be chosen based on workload characteristics, not the other way around. Memory pressure is the key constraint tying together concurrency, batching, and latency. Understanding these interactions is essential for managing serving performance under real load. As context length grows, each request consumes more memory. Larger batches improve throughput, but require more temporary state. High concurrency risks saturating memory, causing queues and longer tail latency. Optimizing one metric often worsens another. A model may appear fast in benchmarks with single requests, but real deployments serve many users and long conversations simultaneously. Memory pressure can force serialized requests or reduced batching, causing users to experience waiting even if the model is fast alone. Batching is often seen as a pure win, but memory and latency constraints limit its effectiveness. Larger batches increase total tokens per second, but delay individual request service. Under memory pressure, the backend must balance concurrency and tail latency carefully. Long-lived conversations allocate context and cache state that compete with other sessions. When many users are active, the backend may evict or delay requests to avoid exceeding memory limits. This means actual serving capacity is often lower than model specs suggest. For few long sessions, a backend handling large contexts well may be best. For many short sessions, aggressive batching may be preferable. For branch-heavy agents, cache-aware memory management matters most. The key question is how the system behaves as live requests grow and change, not just raw model speed. Open source serving engines differ primarily in the workloads they handle well. Understanding these differences helps choose the right backend for your product's traffic and usage patterns. VLLM is a strong generalist for many simultaneous requests, making it a natural default for responsive agent deployments. TGI integrates well with Hugging Face tooling, simplifying pipelines. SGLang shines when branching conversations and cache reuse across forks are important. Each backend suits different workload patterns rather than abstract quality rankings. For single-turn queries or many independent users, a high-concurrency backend like VLLM fits well. If the app uses Hugging Face tools, TGI simplifies integration. For workloads with many branching paths, Sklang's cache-oriented design improves reuse. The backend should match the workload, not just be the fastest on paper. Backend implementations change over time, shifting performance characteristics. What was fastest in one version may not be in another. Teams need stable operational behavior aligned with product concurrency, context, and branching needs rather than relying on outdated reputations. All three engines can present an OpenAI-compatible API, letting the application code remain unchanged while the backend switches underneath. This separation allows infrastructure teams to tune serving independently and experiment with different backends without rewriting agent logic. A better backend can make the same model feel faster and more stable without changing its answers. Conversely, a poor backend can make a strong model feel sluggish. Serving architecture often determines whether the product feels polished, focusing on responsiveness and consistency rather than model internals. Diagnosing workload shape is the most reliable way to select a backend. Traffic steadiness, burstiness, conversation length, and branching all influence which serving system fits best. If traffic is steady with similar requests, throughput and predictability are key. Bursty traffic makes cold start and scale to zero behavior critical. Long, prefix-heavy conversations benefit from cache reuse. Frequent branching demands backends that preserve shared computation. The workload shape should drive backend selection. Atlas can exhibit short, steady lookups, longer prefix-heavy comparisons, branch-heavy planning, and bursty consumer traffic. No single backend dominates all cases. Identifying which workload shape matters most to your users guides the best backend choice. If instant first response is critical, startup and warm latency dominate. If infrastructure cost matters, scale to zero and capacity density take priority. Workloads that reuse prefixes benefit from prefix caching. Branch-heavy workloads prioritize branching performance. Choosing a backend without these metrics is like treating symptoms without diagnosis. Focusing on workload fit helps avoid overreacting to unrepresentative benchmarks or ignoring costly user patterns. A backend that wins benchmarks may fail under real request patterns. For agents with long prefixes and multi-turn flows, workload fit is more informative than headline speed. Using OpenAI-compatible APIs lets the application remain backend agnostic. This separation simplifies experimentation, rollback, and benchmarking by isolating backend choice from agent logic. The agent communicates through a stable API, while backend selection happens through configuration. This reduces the cost and risk of switching backends and keeps reasoning and tool use logic untouched. Configuring base URLs and start commands for each backend lets you swap servers without rewriting agents. This design promotes reproducibility and auditability of deployments. This figure illustrates how the agent interacts with a stable API, while configuration determines which backend, VLLM, TGI, or SGLang, runs behind the scenes. This separation supports flexibility and maintainability. This configuration dictionary maps backend names to their base URLs and star commands. Each backend has a specific port and command line that includes model and server parameters. This setup encapsulates deployment details in configuration rather than code. Generating backend invocation from configuration makes deployments auditable and reproducible. It allows teams to log exact server commands, compare backends fairly, and understand performance differences precisely. Consistent API usage lets serving backends be updated or swapped without modifying agent reasoning or tool use code. This separation reduces risk and supports stable production behavior, even as infrastructure evolves. Building server commands programmatically rather than using ad hoc shell scripts makes deployment logic explicit and easier to inspect. This clarity supports better operational control and debugging. This function constructs the command line arguments to launch a VLLM server. Each flag corresponds to a workload constraint like host, port, model, parallelism, memory use, and concurrency. This structured approach encodes serving policy explicitly. Flags like tensor parallel size, GPU memory utilization, max model length, and max sequences define how the server partitions work, manages memory, and limits concurrency. Disabling log stats reduces overhead during benchmarking. Together, these flags form a compact statement of serving policy. Starting the backend as a process handle rather than a hidden shell command gives clear boundaries for warm-up and logging. This explicit lifecycle control supports better operational management and performance measurement. This function launches the VLLM server process with the constructed arguments, redirecting output to a log file. It prints the process ID and command for auditing. This approach supports controlled startup and monitoring. Explicit launch lets teams measure cold and warm performance under consistent conditions. It also provides an auditable record explaining why particular backend configurations were chosen, improving trust and reproducibility. VLLM's configuration settings should be seen as controls that shape how the server handles workload, balancing capacity, memory, and concurrency to meet product goals. GPU memory utilization limits device occupancy. Tensor parallel size partitions the model, affecting capacity and communication. Max model length sets context limits. Swap space provides overflow memory at a speed cost. Max sequences cap concurrency. Disabling logs reduces overhead during benchmarking. These settings interact and must be tuned together. Increasing context length raises memory per request, reducing concurrency headroom. Raising concurrency may improve throughput, but can increase tail latency under memory pressure. More swap space helps bursts but slows response. These knobs form a negotiated boundary balancing responsiveness and capacity. The serving system controls not just what the model can do, but how much it can do simultaneously without collapse. It enforces limits to keep the service responsive under load, acting as a policy engine balancing capability and stability. Atlas needs a server that can handle many long conversations simultaneously without degrading first token latency or tail latency. These goals differ, and tuning knobs represent how the team negotiates trade-offs to meet user experience requirements. Measuring serving performance under realistic conditions is essential before making claims about backend quality or speed. Single request benchmarks can be misleading because they don't capture concurrency, memory pressure, or request overlap effects. Proper benchmarking includes cold start, warm request, and concurrency profiles matching real agent workloads, including prompt lengths and branching. A large difference between cold start and warm request latency shows serving operates in two regimes. This gap is a hard reality that benchmarking makes impossible to ignore, guiding decisions about scale to zero and warm pools. A backend's performance depends on configuration. Poor tuning can make a good backend look bad, and vice versa. Benchmarks must reflect the exact runtime configuration plan for production to be meaningful. Serving performance should be monitored continuously. Measure cold start, throughput, and concurrency regularly, especially after backend or configuration changes. Adjust runtime parameters before altering product expectations. Once serving is understood, focus can shift to hardware efficiency improvements like compression and quantization. This topic explores how quantization, prompt length, and cache management interact to shape the performance and cost of serving large language models. Understanding these factors helps optimize deployment decisions and resource use. Quantization is often seen as simply reducing numerical precision, but it's more useful to think of it as changing the deployment capacity. It affects model size, memory use, and whether a GPU can run the model at all. Choosing a quantization level determines how large the model checkpoint is and how much VRAM it uses. If the checkpoint is too large for a device, the model simply can't run there. This shifts the problem from tuning the decoder to selecting suitable hardware that can host the model reliably. This figure illustrates how quantization reduces the size of the model weights that must stay in memory. That frees up VRAM for activations and cache, allowing the model to fit on smaller or less powerful GPUs that might otherwise be unable to host it. Treat quantization as a strategic choice that influences more than just model precision. Smaller checkpoints load faster, require less expensive GPUs, and leave more memory for other tasks. This can enable simpler hardware setups without changing the model itself. Quantization compresses model weights, freeing memory like folding clothes more tightly. But if the prompt or cache grows, it fills the freed space. So compression must be balanced with prompt size and traffic patterns to avoid negating the memory gains. The decision to quantize hinges on whether the hardware benefits and cost savings outweigh any loss in model fidelity. Some applications prioritize availability and cost over perfect accuracy, while others need high precision to maintain complex reasoning and stable outputs. Next, we'll examine the scenarios where quantization improves deployment and where it risks degrading model quality in ways that matter operationally. Mild compression often keeps the model accurate enough for classification, routing, or drafting tasks, especially when humans review outputs. This trade-off can reduce infrastructure costs and improve hardware compatibility without harming overall service quality. Strong compression can cause the model to miss constraints, mishandle rare cases, or lose consistency across turns. This is especially problematic when outputs trigger downstream actions or encode critical structured data, where even small errors are costly. If the application is suggestion-based or heavily supervised, small quality losses may be acceptable. But for workflows needing precise reasoning and state tracking, even subtle errors from lower precision can degrade performance or reliability. Short smoke tests can hide quality issues because prompts are familiar and answers easy. Real workloads with longer context and varied instructions expose weaknesses, making it essential to validate quantization against actual usage patterns, not idealized queries. Now we'll look at how checkpoint size influences overall serving cost, including startup latency and operational flexibility beyond just memory use. A smaller model loads faster from disk and initializes more quickly, which lowers cold start delays. This matters whenever workers restart or auto-scaling adds capacity, improving user experience by reducing wait times for the first token. When models load quickly, restarts cause less disruption, new instances become productive sooner, and scaling costs drop. This enhances reliability, especially for customer-facing services where even brief outages are noticeable. Extra VRAM allows the backend to aggregate requests more effectively, retain larger caches, and avoid memory bottlenecks during traffic spikes. This leads to smoother throughput and fewer sudden drops in service quality. If quality remains acceptable, smaller checkpoints reduce fleet costs and simplify scaling. But if compression causes errors, the system may incur extra costs from retries, clarifications, or fallback models, making the cheapest checkpoint not always the cheapest service. Next, we'll examine how increasing prompt length affects serving latency and resource use throughout the entire request lifecycle. Before generating output, the model processes the entire prompt during pre-fill to compute reusable representations and fill the cache. Longer prompts mean more pre-fill work, directly increasing the delay before the first token appears. Large system messages, policy scaffolds, or conversation histories increase computation upfront. Users perceive this as waiting, even though it's part of the model's necessary preparation before responding. The prompt isn't just a startup cost. It stays in memory and influences every token generated. Larger active context means more memory usage and more backend work to maintain sequence semantics throughout decoding. Reducing repeated instructions or stale history lowers pre-fill work and cache size. Optimizing prompt length often yields bigger performance gains than speeding up the decoder alone, making prompt discipline a key serving optimization. This figure highlights how longer prompts expand the pre-fill computation and cache size, directly extending the delay before the model starts generating. It shows why prompt length impacts serving latency and memory use. Additional context often raises answer quality by providing more information. The goal is to keep only the history that influences the next decision, ensuring the serving stack can handle the workload efficiently without unnecessary bloat. Now we'll explore how the key value cache used during decoding creates memory constraints that affect concurrency and latency, especially under heavy load. This cache avoids recomputing representations on each decode step, but increases memory use as context grows. Larger caches reduce available VRAM for other requests, limiting how many can run simultaneously. When memory fills, the backend must decide which requests stay resident and which wait or get evicted. This impacts unlucky requests disproportionately, causing some to slow down sharply while average latency may look stable. Short requests can complete quickly, but long conversational requests consume much cache space, reducing how many requests fit in memory. The GPU then acts as a memory gate, not just a compute engine, limiting throughput under load. As the cache fills, the backend's ability to batch requests efficiently declines, leading to fragmented memory and uneven performance. Users often notice this as inconsistent quality and slow responses in the worst cases. Prefix caching optimizes repeated prompt prefixes by reusing cached key-value blocks, reducing prefill work for stable shared segments. When many requests share the same opening prompt segment, the backend can reuse cache computations for that prefix instead of recalculating them each time, lowering latency and compute load. Support systems often send identical instructions and tool definitions repeatedly, differing only in user messages. Prefix caching avoids repeating the full prefill cost for these stable parts, improving responsiveness and throughput. This configuration does not create reuse by itself, but allows the backend to detect and cache repeated prefix segments. When enabled and the workload fits, it can substantially reduce prefill work and improve latency. The optimization benefits shrink rapidly if requests diverge soon after the prefix. It only amortizes the cost of the truly repeated segment, so it's most effective when the shared prefix is large and the unique tail is small. Now we'll discuss why prefix caching sometimes fails and the practical limits on cache reuse in real deployments. Even minor differences like timestamps, request IDs, or session data break exact prefix matches, forcing the backend to recompute cache blocks. This is a common cause of disappointing caching results despite apparent prompt similarity. When the prefix changes, the backend loses cache state and must redo computations. Differences in latency across similar requests often reflect how stable the shared prefix is, making observability of prefix reuse critical. Even with identical prefixes, cache blocks can be evicted to free memory for new requests. This means caching is opportunistic and depends on memory headroom and traffic patterns, not a guaranteed speedup. It struggles when prompts diverge quickly, injected context changes often, or cache churn is high due to concurrency. Effective reuse requires both traffic stability and sufficient memory resources. Next, we'll look at paged KV caching, a memory management technique that helps handle variable request lengths more efficiently, but cannot overcome physical memory limits. Instead of treating cache memory as one big block, paging breaks it into smaller pieces that can be allocated independently. This reduces fragmentation and improves how the backend fits active sequences into VRAM. When requests differ in length, contiguous cache layouts can leave holes that waste memory. Paging packs sequences more tightly, allowing more requests to run concurrently and making latency more consistent under varied loads. Better memory organization helps use VRAM more efficiently, but does not create extra memory. Teams must avoid mistaking paging gains for permanent capacity increases, as hardware limits still apply. Paging makes serving more resilient to variable request sizes and memory pressure, helping the backend degrade gracefully. However, it cannot replace the need to manage checkpoint size, prompt discipline, and workload patterns within hardware limits. Finally, we consider how to balance model size, prompt length, and hardware capacity to optimize serving performance and cost. First, check if the model fits on the hardware at the desired precision. If not, quantization can reduce size. Next, see if prompts can be shortened to improve performance. Finally, if memory and concurrency demands exceed capacity, upgrading hardware may be necessary. Support assistance with repeated instructions and tool definitions can leverage prefix caching effectively. Moderate quantization helps reduce latency and cost without sacrificing too much quality, making smaller checkpoints and cache-aware prompts advantageous. When requests include long documents, shifting instructions, or prompt edits, caching is less effective and memory demands rise. In such cases, maintaining higher precision and investing in bigger hardware often yields better reliability. Teams sometimes expect quantization to solve all problems without quality loss, overlook prompt repetition that wastes resources, or mistake temporary cache limits for persistent memory issues. Correct decisions start by identifying the true bottleneck and choosing the right lever accordingly. These three levers interact closely. Gains from quantization vanish if prompts grow immediately. Shortening prompts helps only if essential information is preserved. Larger hardware absorbs more load, but increases cost. Often, reducing repeated input at the front of requests offers the easiest and most effective improvement. We conclude with practical guidelines to diagnose performance issues and prioritize tuning efforts based on symptom patterns. If all requests start slowly, the problem is likely model size or loading cost. If only long conversations slow down, context length and KV cache are the bottleneck. When the same request varies in speed, prefix caching may be failing due to unstable prefixes or eviction. If output quality degrades in areas needing precision, compression is likely too aggressive. If quality is fine but latency is high, the serving infrastructure is the cause. Distinguishing these helps avoid trading quality for speed unnecessarily. When tail latency grows faster than average, memory contention is increasing. If cache hit rates fluctuate despite stable workloads, prompt instability is often the culprit. Standardizing shared prompts can improve reuse and performance. Duplicated instructions or policies increase memory and latency costs unnecessarily. Shortening and stabilizing front matter can yield bigger gains than complex backend optimizations. Quantization, context growth, and cache behavior are interconnected forces that shape whether an agent serves users responsively and cost-effectively. This part focuses on understanding measurement from two distinct perspectives: the serving stack's performance and the agent's quality. Recognizing this difference helps avoid confusion when diagnosing issues in production systems. A production agent is evaluated both on how well it performs its task, being useful, correct, safe, and aligned, and on how well the serving infrastructure delivers its responses with acceptable speed, capacity, and cost. These two aspects are only loosely connected. A backend can be technically solid but produce poor results, while a great agent can be hampered by slow or costly delivery. Mixing these concerns makes tuning and debugging much harder. This figure highlights the separation between agent quality and serving stack performance. Agent quality focuses on the content and correctness of the model's output, while serving stack performance measures how efficiently and reliably the backend delivers those outputs to users. Serving stack benchmarking should focus on operational questions like how the backend behaves under repeated, concurrent requests with realistic prompts. The goal is to understand latency, throughput, and scalability, rather than whether the agent's answers are correct. This keeps infrastructure tuning grounded in practical performance goals. Metrics like latency and throughput mean different things depending on the context. In serving benchmarks, latency measures request path speed and throughput measures backend capacity. In agent evaluations, latency is part of the cost of getting a useful answer, and throughput matters only if it affects user experience or test coverage. The same data trace can serve both purposes but must be interpreted accordingly. For example, the Atlas Travel Assistant might have excellent reasoning, but feels slow if the serving stack delays the first token. Or it might handle single requests well, but fail under concurrent load, making it seem unreliable. Measuring serving performance separately removes uncertainty, so agent evaluations can focus on what the model actually knows and decides. Choosing the right benchmark target means deciding exactly what question the product needs to answer. This focus guides how we measure performance and what results matter for the product's success. Benchmarks work best when they begin with a clear, focused question about the product's behavior. Without this, teams risk collecting many metrics that don't clarify what the product actually needs to achieve or improve. We evaluate backend performance through three perspectives. Latency reflects user experience in interactive settings. Capacity measures how many requests the system can handle before slowing down. Economics translates performance into resource use and cost. Balancing all three is essential for a practical product. This figure illustrates how different traffic patterns highlight distinct failure modes. Latency tests focus on response speed, capacity tests on concurrency limits, and economics tests on cost efficiency. Each lens reveals unique insights about backend behavior under various conditions. The pattern of traffic affects what the benchmark reveals. Steady traffic tests efficiency during normal operation. Bursty traffic challenges the system's ability to handle sudden spikes. Startup-heavy traffic examines how quickly the system recovers from restarts or scaling events. Ignoring these shapes risks optimizing for the wrong scenario. Defining clear pass and fail criteria before running benchmarks ensures the results help choose the best backend for the product. These criteria should reflect real product needs, like latency budgets and concurrency stability, rather than just chasing the highest scores. This part focuses on how to apply our running example to create a clear and practical measurement setup. Understanding this helps us see how benchmarking works in a real application context. The Atlas Travel Assistant is a great choice for benchmarking because its workload involves conversation, keeps some state, and depends heavily on quick responses. It doesn't require special tools just to test if a backend can handle prompts effectively. By replaying the same prompt, context, and conversation state across different backends, we isolate the backend's impact on performance. The benchmark harness must closely imitate the real product's request pattern, including system instructions and state format. This way, we can swap out the serving backend without changing the agent's logic. The application shouldn't notice the difference, which lets us measure the backend's behavior as a drop-in replacement, preserving engineering flexibility. Using a reusable benchmark setup lets the team compare how the backend performs under steady conditions and during bursts of requests. A scripted run can control request rates, measure response times, and reveal how concurrency affects performance. Since the application logic remains fixed, any differences come from the backend, not from changes in prompts or agent behavior. Starting the backend with explicit configuration commands makes benchmarks reproducible by design. The same application code can be tested with different launch profiles, such as low latency or memory-efficient modes. This separation between application logic and serving configuration allows teams to tune backend performance systematically instead of relying on ad hoc manual changes. Understanding these four core signals is essential for evaluating backend performance. Each one reveals different aspects of how a system responds under real-world conditions. Latency is the most familiar metric, but it requires careful interpretation. The average latency tells you about a typical request, but typical doesn't mean acceptable. Some users might experience long delays, even if the mean looks good. For interactive agents, the time until the first token appears matters more than the total time, because seeing a response start quickly reassures the user and improves perceived speed. Throughput shows how many requests a backend can complete over time when it's busy. It's important when multiple users or rapid requests happen simultaneously. A system might be fast on one request, but still fail to handle many at once if it processes requests sequentially or uses resources inefficiently. Throughput reveals whether a backend can handle real usage or just perform well in demos. Concurrency tests how a backend behaves when several requests happen at once. Some systems maintain stable latency until a limit is reached, then degrades suddenly. Others slow down more gradually. The shape of this degradation curve matters because it shows if the system's capacity is manageable or brittle. Treating concurrency as a primary variable helps expose hidden weaknesses that single request tests miss. Tail latency focuses on the slowest responses, which often shape user trust more than median speeds. Even if most requests are fast, occasional long delays can feel unreliable. These delays often result from hidden queuing or resource contention. Evaluating tail behavior ensures the backend feels responsive not just usually, but consistently, especially under less ideal conditions. These signals shouldn't be combined into a single number too early because each reveals different trade-offs. For example, increasing batching might boost throughput but worsen first token latency. Adding memory headroom can stabilize tail latency but reduce efficiency. A thorough benchmark looks at all these metrics together to reveal trade-offs before they impact users. Startup and cold start behavior affect user experience differently from steady-state performance. This part explains why measuring them separately is essential for understanding real-world responsiveness. When a backend is already running and the model is loaded, it can respond quickly to requests. But the first request after a deployment or scaling event often faces a much longer delay. This startup delay is a distinct user experience issue, especially in systems that scale dynamically or deploy frequently. Metrics that only show fast response times when the system is hot can be misleading. A backend might look excellent on dashboards, but still impose a long wait during initialization. This cold start acts like a first impression tax, paid once per launch, and it can shape user perception more than many fast responses afterward. For example, in the Atlas Travel Assistant, cold starts happen after fresh deployments, quiet periods, or regional failovers. Users care about response time right away, not after the system warms up. Measuring startup latency separately helps compare deployment strategies and choose backends that balance steady-state speed with quick readiness. If startup time is significant, teams might avoid scaling to zero, maintain a warm pool of instances, or pre-warm before peak usage. These decisions come from understanding the hidden costs of cold starts, ensuring deployment choices reflect actual user experience rather than simplified averages. This part focuses on the configuration settings that have a real impact on model serving performance. Understanding these knobs helps us tune latency, capacity, and memory behavior to meet product needs. Performance during serving isn't just about the model's design. The backend system and how it's configured can significantly affect latency, capacity, and memory usage. Treating the backend as a controllable system rather than a black box allows us to optimize these factors effectively. Tensor parallelism controls how the model is distributed across hardware, enabling larger models or fitting models onto available resources. However, it can add communication overhead. GPU memory utilization sets how much device memory is used, balancing capacity and safety margin. Maximum model length limits the context size, affecting both capability and memory pressure. Swap space can relieve memory pressure by offloading data to slower storage, but may cause unpredictable delays. Batching capacity improves throughput by grouping requests but can increase wait times. Precision mode trades off memory and speed against quality. Excessive logging adds overhead that can slow down the serving loop, especially under load. These operational settings also shape how the user perceives the agent. Optimizing for throughput might delay response start times, while tuning for responsiveness can waste hardware capacity. The best configuration aligns with traffic patterns and product goals, so benchmarking should focus on user-facing outcomes, not just server metrics. Think of each configuration knob as adjusting the response curve differently. Some lower the minimum latency, others raise the maximum capacity, and some change how performance degrades under heavy load. High-tail latency often points to memory or batching issues, while low single request latency with poor throughput suggests idle hardware or batching inefficiencies. Visibility and control of these variables are essential for meaningful interpretation. This part explains how to turn benchmark data into a clear sequence of tuning decisions. Understanding this helps us move from just gathering numbers to actually improving system performance in a controlled way. Benchmark results are only useful if they lead to changes in configuration. If the data just sits in a report without prompting adjustments, it's merely an observation, not part of a tuning cycle. The process should be simple. Measure under consistent conditions, find which metric is off, adjust one variable, and test again. This discipline prevents confusion and contradictory conclusions. The key rule is to adjust only one variable at a time. For example, if latency is too high, you might increase batching only if hardware isn't fully used. If tail latency worsens with concurrency, you could reduce request size or increase memory headroom. If cold start is slow but warm performance is fine, focus on deployment strategy. Each change should test a specific idea, not guess randomly. Back-end tuning often involves trade-offs that don't show up in average numbers. A setting might reduce average latency, but worsen worst-case delays. Another might boost throughput, but increase startup time or memory use. If benchmarks separate these factors, the decision tree can prioritize based on product needs. For instance, a live assistant might accept lower throughput for faster first responses, while a batch service might prefer throughput over latency. A strong benchmark report ends with a clear recommendation, not just numbers. It should identify the best configuration for the traffic pattern, explain which metric influenced the choice, and describe any accepted trade-offs. This connects measurement to readiness for production. A mature serving stack can explain both what was measured and why a specific configuration was selected, along with conditions to revisit that choice later. Different traffic patterns require different serving strategies. Understanding these patterns helps us choose the best backend setup for each scenario. A steady workload benefits from stable throughput and efficient use of resources, where small inefficiencies are less harmful than instability. Bursty workloads, however, require the system to handle sudden spikes in concurrency without failure. When workloads involve frequent restarts or scaling, readiness time becomes critical since cold starts affect user experience directly. Traffic for a product like Atlas Travel Assistant can vary throughout the day. During planning hours, traffic might be steady and moderate, but a promotion or travel disruption can cause sudden bursts. A backend optimized for steady use may struggle with bursts, while one designed for bursts might waste resources during steady periods. Benchmarking must consider these demand shifts to choose the right tuning. Not all backends are interchangeable. Some excel at quick startup and light interactive traffic, others at sustained batching and high concurrency. Some are suited only for large models where memory partitioning matters. The best backend matches the product's traffic pattern, hardware limits, and latency goals, just like selecting the right gearbox for different driving conditions. Benchmarks should use traffic profiles that reflect real usage. Low concurrency tests show baseline responsiveness. Burst profiles reveal when queuing begins, and start-restart profiles expose deployment overhead. Measuring these separately helps pick a backend strategy aligned with the dominant traffic mode rather than a single aggregated number. Performance numbers depend heavily on the underlying hardware and its cost. This part explains why evaluating backend speed alone is not enough and how cost and hardware constraints shape real-world performance. Hardware always imposes a minimum cost that you cannot avoid. A backend that looks fast might require a more expensive GPU or more memory, which affects the overall system budget. Conversely, cutting costs by pushing hardware limits can increase latency in ways that harm user experience. So, benchmarks must be understood as conversations about both budget and technical performance. Larger models typically need more memory and compute power. The hardware you choose determines how much of that demand can be handled directly and how much requires backend techniques like parallelism or batching. If a model barely fits on a GPU, it might pass benchmarks but struggle under real concurrent load. When there's enough hardware headroom, latency tends to be more stable and predictable. Benchmark results should be seen as trade-offs between cost and performance. For example, if a travel assistant meets latency goals on smaller hardware, that might be preferable to a faster backend that doubles costs. When larger models are needed, tuning the serving stack around their resource needs matters more than just chasing raw speed. The key question is which backend delivers the right experience at an acceptable cost with enough stability. Scaling hardware by intuition alone can be risky. Choosing the most powerful hardware may hide inefficiencies and create expensive baselines, while underestimating needs can cause missed responsiveness under load. Benchmarking grounds these decisions in measured behavior, avoiding guesswork and marketing claims. Creating a reproducible launch pattern for backend servers helps maintain consistency across benchmark runs. This approach ensures that experiments can be repeated reliably, which is essential for meaningful comparisons and tuning. Benchmarks lose value if their results can't be repeated under the same conditions. When backends are started manually with random flags, it becomes impossible to compare runs fairly. By automating launch commands and configurations, the server setup becomes a controlled part of the experiment, like a lab instrument rather than a one-off shell command. This configuration dictionary defines how to launch different backends in a reproducible way. Each backend has a base URL and a templated start command with placeholders for model and name. This structure centralizes launch details and makes switching or updating backend straightforward. These constants define parameters for launching the VLLM backend. They include network settings like port and host, resource controls such as tensor parallel size and GPU utilization, and flags for model length and logging. Keeping these parameters centralized helps maintain consistent launches. This function assembles the command line arguments to launch the VLLM server. It uses the constants and parameters to build a list of flags, ensuring that every launch uses the same baseline configuration. Additional arguments can be appended to customize runs without changing the core setup. This function starts the VLLM server as a subprocess using the command built earlier. It redirects output to a log file for later inspection and prints the process ID and full command for traceability. This controlled launch allows the benchmark harness to manage server lifecycle programmatically. The real benefit of this launch pattern lies in the discipline it enforces. It lets teams compare different backends without touching application code and rerun experiments with different parameters while keeping everything else constant. This makes tuning results scientifically valid and reproducible. Using an OpenAI-compatible endpoint means the serving backend can be swapped without rewriting the agent. This separation makes the benchmark portable and production-ready, turning it into a repeatable framework rather than a manual checklist. This part explains how benchmarking relates to deployment maturity and what comes after it in the development process. Understanding this connection helps clarify when and why performance measurement matters. Back-end benchmarking is a key milestone because it shows when decisions start relying on real data instead of guesswork. A prototype that only works on one machine hasn't proven can handle real-world demands like traffic load or resource limits. A production-ready system, however, has been tested and optimized based on actual usage patterns and cost constraints. This reflects a broader model where each measurement step reduces uncertainty and moves a project closer to a reliable service. It's important to understand what benchmarking cannot tell you. It can confirm that your system is fast, scalable, or cost-effective, but it doesn't evaluate whether the agent provides good advice, handles errors well, or follows policies correctly. Those are separate evaluation questions about the agent's behavior. Confusing backend performance with agent quality leads to mistakes, since a system can run smoothly yet still produce poor results. Evaluating the agent's behavior becomes more reliable once the serving stack is stable. If the backend is still changing unpredictably, the noise from performance fluctuations can distort quality measurements. By first measuring and tuning the serving layer, you create a stable foundation that makes evaluation meaningful. So, benchmarking is not the final step, but a necessary stage where infrastructure uncertainty is minimized. Think of the serving stack as a traffic transformer that converts raw modelability into responsiveness, concurrency, and operating cost. Benchmarking checks if this transformation is efficient enough for your product goals. Evaluation then asks whether the output, after this transformation, actually meets quality standards. Keeping these two steps distinct is essential for disciplined production development.